Galaxies are not what they appear to be. They are not random collections of stars, but intricate structures held together by an invisible hand. This is the reality of dark matter, the hidden architecture beneath every galaxy. For decades, astronomers have known the universe we see is only a fraction of what exists. An unseen blueprint of dark matter provides the gravitational scaffolding for everything we observe. By the end of this video, you will understand how this invisible framework shapes the cosmos and why it is fundamental to our own existence. We will uncover how a substance we cannot see dictates the fate of galaxies and holds the key to the universe's grand design. What do you think it means for our place in the cosmos? A magnificent cathedral would collapse without its unseen supports, and so too would a galaxy. This invisible framework is dark matter, a substance that fundamentally does not interact with light. It is completely transparent to every form of electromagnetic radiation we use to see the cosmos. We cannot photograph it, scan it, or observe it directly with any telescope ever built. Yet its gravitational pull is undeniable, a force that sculpts the universe on the grandest scales. This realization began not with sophisticated modern tools, but with a single astronomer's perplexing observation nearly a century ago. His name was Fritz Zwicky, and he was studying the Coma Cluster, a vast collection of galaxies hurtling through space. By measuring how fast these galaxies were orbiting the cluster's center, he made a shocking discovery. They were moving far too quickly. According to the laws of gravity and the amount of visible mass Zwicky could count, the galaxies should have been flung apart, escaping the cluster's feeble gravitational grip. They were not. Something unseen, a tremendous amount of invisible mass, was providing the extra gravity needed to bind the entire cluster together. Zwicky called this missing material dunkle materie, or dark matter. For decades, his idea was largely dismissed as an oddity, but the mystery would not go away. It was the first crack in our understanding, a hint of the vast, hidden architecture waiting to be uncovered. The quiet halls of Caltech in the 1930s were home to a mind that saw the universe differently. Fritz Zwicky, a brilliant and often contentious astronomer, was meticulously studying the Coma Cluster, a sprawling metropolis of over 1,000 galaxies. He began with a simple calculation, adding up all the mass he could see from the glow of countless stars. The result should have told him how strongly gravity was holding this cosmic city together. But when he measured how fast the individual galaxies were actually moving, he was met with pure astonishment. They were racing around at speeds that defied logic. According to the known laws of physics and the total visible mass, the cluster's gravity was far too weak to prevent these galaxies from flying off into the void. Yet they remained bound together, a swirling dance that should not have been possible. Something was providing an immense, unseen gravitational anchor. Zwicky proposed the answer was a vast amount of missing material, which he named dunkle materie, dark matter. His radical idea was a direct challenge to the comfortable belief that the cosmos was made only of what shone in our telescopes. For decades, his work was largely pushed aside, seen as an anomaly or a miscalculation. But this was the first historical clue, a profound indicator that our cosmic inventory was woefully incomplete. The hidden architecture had been glimpsed, and the evidence for its existence was only beginning to accumulate. The ghost in the cosmic machine refused to stay hidden. Decades after Fritz Zwicky's puzzling calculations, a new generation of astronomers began to see its fingerprints everywhere. It was Vera Rubin, working quietly with a telescope at the Carnegie Institution, who would finally give this ghost a shape. Her target was the beautiful spiral of the Andromeda Galaxy, our nearest major galactic neighbor. She set out to map its rotation, to clock the speed of stars and gas clouds as they traced their circular paths around the galactic core. She expected to see a very familiar pattern. In our own solar system, the planets orbit the Sun according to a simple rule. Mercury, close to the Sun's fierce gravity, whips around at a blistering pace. Neptune, out in the frozen depths, moves at a comparative crawl. Rubin anticipated the same behavior in a galaxy. Stars near the bright, crowded center should race along, while those in the sparse outer regions should orbit much more slowly, their speed falling off in a predictable decline. What she found, however, defied every expectation. The stars far from the luminous center were not slowing down. Their orbital speeds remained stubbornly high, a flat line on her graph that stretched far beyond the galaxy's visible edge. It was as if every planet in our solar system, from Mercury to Pluto, orbited at the exact same velocity. This was the famous flat rotation curve, a result that was both simple and revolutionary. The only possible explanation was a breathtaking one. Spiral galaxies like Andromeda are not just disks of stars. They are embedded within immense, spherical halos of invisible matter, halos that extend far beyond the last visible star. This dark halo provides the extra gravitational tug, pulling on the outer stars and forcing them to maintain their unexpected speed. Vera Rubin had not just found evidence for dark matter, she had proven it was a universal component of galaxies, the hidden foundation upon which every spiral is built. Her work in the 1970s transformed a fringe concept into a cornerstone of modern astrophysics. We now knew the dark architecture was real, woven into the fabric of every galaxy. But knowing it exists is one thing. How do you map something you cannot see? The challenge of mapping an invisible substance seemed impossible, yet astronomers found a way to use the universe itself as a tool. They turned to a cosmic illusion predicted by Einstein, a phenomenon called gravitational lensing. Think of the fabric of space-time not as a rigid stage, but as a vast, flexible sheet. When a tremendous mass, like a cluster of galaxies, sits in this sheet, it creates a deep gravitational well. Light from a distant galaxy traveling toward us does not move in a straight line as it passes this well. Instead, its path curves, bending around the massive object. This turns the entire galaxy cluster into a natural telescope, a cosmic magnifying glass. The result is a spectacular distortion. The images of galaxies far behind the cluster are stretched and warped into long, faint arcs and sometimes even complete rings of light, known as Einstein rings. These are not tricks of the camera. They are the direct signature of gravity warping the very path of light itself. By meticulously studying the precise shape and degree of these distortions, scientists can perform a remarkable feat. They can calculate exactly how much mass in the foreground cluster is causing the bending and, crucially, where that mass is located. This allows them to create a map of all the mass present, both the visible stars and the invisible dark matter that makes up the bulk of the cluster's gravity. The maps that emerge are breathtaking. They reveal a hidden architecture of dark matter woven through the cluster in vast, intricate webs and filaments. This is the cosmic skeleton, the framework upon which the luminous galaxies are draped like ornaments on a tree. Projects like the Hubble Space Telescope's frontier fields have used this powerful technique to stare into the deepest reaches of space and time. They have uncovered dark matter structures that existed when the universe was young, tracing the growth of this invisible blueprint over billions of years. So while we cannot see dark matter directly, we can watch how it bends the light from distant galaxies, revealing its shape and distribution with stunning clarity. The patterns etched by this light tell us that dark matter is not a featureless cloud. It has a specific, clumpy structure, a clue that points toward its fundamental nature and pushes us to ask the next great question. What exactly is this mysterious substance made of? So we have the map of this invisible architecture, but its fundamental ingredient remains a ghost. What could this substance possibly be made of? The hunt for the particle itself is one of the greatest scientific quests of our time, and it has led physicists to two prime suspects. The first are known as WIMP, an acronym for Weakly Interacting Massive Particles. Imagine a particle that is heavy, perhaps dozens or even hundreds of times the mass of a proton, yet it is utterly aloof. It feels gravity, and it interacts through the weak nuclear force, the same force responsible for certain types of radioactive decay, but it is completely blind to light and electromagnetism. It would pass through our planet and through you as if they were not even there. For decades, WIMP have been a favorite candidate because of an elegant cosmic coincidence. Calculations of how many of these particles would have been forged in the searing heat of the Big Bang, and how many would have survived to the present day, yield an amount that perfectly matches the dark matter we observe. It is a solution that is almost too beautiful to be true. The other leading candidate is at the opposite end of the scale, a particle called the action. Actions are theorized to be incredibly light, billions or even trillions of times lighter than an electron, behaving less like a single speck and more like a pervasive, ghostly wave washing through the cosmos. They were first proposed to solve a deep puzzle in particle physics concerning the symmetry of forces, but researchers soon realized that if they exist, they could also flood the universe, collectively making up the dark matter. The search for these phantoms is as ingenious as the theories themselves. To find a WIMP, you must build an exquisitely sensitive trap, deep underground, in abandoned gold mines or beneath mountains. Experiments like LUX Zeppelin and Xenon NT wait in silence. Their cores are vast vats of ultra-pure liquefied xenon, shielded from cosmic rays by a mile of rock. The hope is that once in a great while, a dark matter particle will, by sheer chance, bump into the nucleus of a xenon atom. The resulting flash of light and ripple of charge would be minuscule, but it would be a signal from the hidden world. The search for actions is different. These wispy particles might be coaxed to reveal themselves in the presence of an immensely powerful magnetic field. Inside specialized detectors, a strong magnet could, in theory, convert a passing action into a faint, specific frequency of microwave light. It is like tuning a cosmic radio to a station that has been broadcasting since the beginning of time, listening for the whisper of a particle turning into a photon. The identity of the dark matter particle is not just a box to check on a physics list. Its properties are written into the very fabric of every galaxy. Whether it is a heavy WIMP or a wave-like action determines how it clumped together in the early universe, how it sculpted the first gravitational wells that would eventually become galaxies, and why it forms those vast spherical halos we see today. Finding the particle means reading the original blueprint. This vast, invisible halo is the true gravitational master of a galaxy. Picture it not as a simple sphere, but as a deep cosmic well. The dark matter is densest at the very center, creating a steep gravitational slope, and then it thins out gradually, its influence stretching hundreds of thousands of light years beyond the last visible star. It is within this unseen well that the entire story of a galaxy unfolds. Ordinary, luminous matter, the gas that will become stars, is drawn into this pre-existing gravitational pit. As the gas sinks to the bottom of the well, it can cool and condense, eventually fragmenting into the brilliant fires we see as stars. The scale of this dark matter foundation dictates everything about the galaxy that forms within it. A truly massive halo, pulling in immense amounts of gas, will likely give birth to a giant elliptical galaxy, a vast sphere of ancient stars. A smaller, quieter halo might become the home for a delicate dwarf galaxy or a graceful spiral like our own Milky Way. Our galactic home is cradled within such a halo, a structure that contains at least 10 times more mass than every star, every planet, and every cloud of gas we can observe. This hidden giant is not a static sculpture, however. It is a dynamic, evolving entity. Over billions of years, dark matter halos grow by merging with one another. A smaller halo might be swallowed by a larger one, its identity lost in a cosmic confluence. These mergers are the great architects of change, often triggering violent bursts of new star formation or dramatically twisting a spiral galaxy into a new shape. The entire life of a galaxy, from its birth to its transformations, is choreographed by the silent, relentless gravity of its dark matter halo. So how did these immense gravitational wells first appear in the emptiness of the early universe? The universe was a seething ocean of energy in its first fleeting moments. Within this primordial fire, the first dark matter particles were likely forged, emerging from the incredible energies of the Big Bang itself. But their nature, their aloofness from light and ordinary matter, set them on a unique path. Because they interact so weakly, they quickly stopped colliding with other particles. They froze out of the cosmic soup, becoming a stable, relic population that would forever permeate the expanding cosmos. This was the raw material, the invisible clay waiting to be shaped. And shape it did, thanks to a crucial head start. The early universe was not perfectly smooth. Minute quantum fluctuations, stretched to cosmic proportions during a period of hyper-fast inflation, created the faintest seeds of density, tiny hills and valleys in the fabric of space. Dark matter, feeling only the gentle pull of gravity, began to slowly accumulate around these slightly denser regions. Ordinary matter, in stark contrast, was trapped. It was a plasma of charged particles, constantly buffeted and pushed apart by the intense pressure of radiation. It could not begin to clump together effectively. So while luminous matter was being scattered by light itself, dark matter was quietly coalescing, building the foundation in the shadows. Over millions of years, these dark matter concentrations grew. What began as tiny ripples evolved into deep gravitational wells, the first dark matter halos. Once these halos reached a critical mass, their gravitational pull became strong enough to overcome the radiation pressure. They began to draw in the swirling clouds of hydrogen and helium gas. This was the pivotal moment. As the gas fell into these pre-existing dark wells, it condensed, heated, and eventually sparked into the first brilliant stars. The very first galaxies were not built from the stars outward. They were ignited within the nurturing cradle of dark matter structures. The specific properties of the dark matter particle, whether it was cold and slow-moving or slightly warmer, dictated how these first halos formed. This determined the size of the first galaxies and the pattern in which they would eventually connect. The entire cosmic story that followed, the majestic spirals and the giant ellipticals, the vast clusters and the great cosmic web, all of it was written into that hidden blueprint in the universe's infancy. This cosmic blueprint extends far beyond the halo of a single galaxy, weaving a structure of unimaginable scale. The universe is not a random scatter of islands, but a single, interconnected metropolis, a vast cosmic web. This is the large-scale structure of everything, and its primary architect is dark matter. Picture an immense sponge with galaxies clustered along dense, interconnected filaments, meeting at massive junctions like cosmic cities. Between these brilliant strands stretch the voids, incomprehensibly vast and nearly empty regions of space. This entire structure emerged from the relentless pull of gravity, acting on the dark matter framework laid down after the Big Bang. Over billions of years, dark matter collapsed into this intricate network, with ordinary matter simply flowing along the pre-drawn lines, pooling at the intersections to form the brilliant galaxy clusters we see. This grand design has been mapped in breathtaking detail by projects like the Sloan Digital Sky Survey, which meticulously charted the positions of millions of galaxies. The resulting three-dimensional maps show this web in all its glory, a filamentary pattern etched across the sky on the largest scales. But how do we know dark matter is the true builder? The proof comes from our ability to simulate the universe. Supercomputer models like the famous Millennium simulation start with the faint ripples of the early cosmos and then let the laws of physics, primarily gravity, play out over cosmic time. When scientists program these simulations with a universe dominated by cold dark matter, the result is a structure that perfectly mirrors the real cosmic web we observe. The simulations do not input the web, they grow it from the gravitational influence of the invisible scaffolding. This vast network is not just a static map, it is a dynamic highway system that dictates the life of every galaxy within it. The filaments act as cosmic conduits, funneling fresh supplies of hydrogen gas from the voids toward the growing galactic halos at the nodes. A galaxy's position within this web, whether it is isolated on a quiet filament or crowded at a bustling intersection, determines its history, its size, and its future interactions. The cosmic web is the ultimate expression of dark matter's hidden architecture, the framework upon which the entire luminous universe is built. The deep gravitational pull of a dark matter halo acts as a cosmic fishing net, gathering the raw materials for creation. Vast clouds of pristine hydrogen and helium, the elemental fuel left over from the Big Bang, are drawn inward by this immense unseen force. As this primordial gas plummets into the halo's gravitational well, it does not fall gently. It collides with itself, creating immense shock waves that heat the gas to millions of degrees, causing it to glow in the X-ray spectrum. For a galaxy to be born, this hot, turbulent gas must find a way to settle. It begins to radiate its tremendous thermal energy away into the cold of space, a slow and crucial process of cosmic cooling. As it loses energy, the gas can no longer resist the relentless pull of gravity. It condenses and sinks toward the halo's center, beginning to spin and flatten into a vast, rotating disk. It is within the cold, dense cores of this swirling gas that the miracle happens. Pockets of gas become so dense and cold that their own gravity causes them to collapse. Deep within these nurturing cocoons, pressure and temperature soar to unimaginable levels until nuclear fusion ignites. A star is born. This entire luminous drama, from the first spark to the brilliant spiral of a galaxy, is orchestrated by the silent, gravitational script of the dark matter halo. The halo's own characteristics, its total mass and even its inherent spin, are permanently stamped onto the galaxy it creates. A halo that gathered mass through a violent, chaotic history of mergers will likely produce a turbulent, featureless elliptical galaxy. A quieter halo, one that grew steadily and with a stable rotation, provides the perfect conditions for a graceful, ordered spiral like our Milky Way to emerge. The efficiency of turning gas into stars is the final brushstroke in this cosmic painting. In some halos, the process is prolific, creating a brilliant starburst galaxy. In others, it is slow and measured, resulting in a more sedate galactic life. Every galaxy we see is a unique expression of its dark matter foundation, a luminous signature written by an invisible hand. The final shape of a galaxy is a story written in gravity and time. Look up at a spiral galaxy like our own Milky Way, and you are witnessing a history of stable, ordered growth. Its elegant arms trace a pattern of sustained rotation, a delicate dance made possible by a dark matter halo that accumulated mass gradually and peacefully. This steady gravitational anchor allowed vast reservoirs of gas to settle into a calm, spinning disk where new stars could ignite in an orderly fashion over billions of years. The spiral structure itself is a density wave, a ripple of star formation perpetuated by the halo's consistent pull. It is a galaxy that has lived a relatively quiet life, its form a testament to cosmic stability. Now contrast this with the colossal elliptical galaxy. These are the featureless giants of the cosmos, immense spheres of ancient red stars. Their smooth, unstructured appearance speaks not of peace but of a violent past. They are often the product of a cosmic catastrophe, a major merger between two spiral galaxies of similar size. When such a collision occurs, it is not a gentle meeting. The orderly, circular orbits of billions of stars are thrown into chaos, randomized into a swirling, chaotic swarm. The vast clouds of gas within both galaxies are not given a chance to settle. They are violently compressed, triggering an explosive firestorm of star birth known as a starburst. This frenzy consumes the available fuel in a relatively short cosmic time, leaving behind a galaxy that is red and dead, filled with aging stars and little gas to create new ones. What happens to their dark matter halos in this colossal event? They merge as well, their invisible frameworks combining to form a single, larger, and more diffuse spherical halo. This new gravitational well is deep, but it lacks the coherent spin that can organize a disk. The entire life story of a galaxy, from its serene spiral arms to its chaotic elliptical form, is fundamentally guided by the history of its unseen foundation. The hidden blueprint of dark matter does not just build galaxies, it sculpts their very identity, leaving its signature in the majestic diversity we see across the sky. But the grand spiral and elliptical galaxies are only part of the story. To truly understand the hidden architecture, we must turn to the smallest and faintest of all, the dwarf galaxies. These tiny, dim collections of stars, often found orbiting larger galaxies like the Milky Way, are more than just cosmic afterthoughts. They are pristine laboratories, fossil relics from the universe's youth that hold the key to dark matter's most subtle properties. According to our most sophisticated supercomputer simulations, the cosmic web should be absolutely teeming with small dark matter clumps. The gravitational collapse of the early universe should have produced a vast population of tiny halos, far outnumbering the dwarf galaxies we actually see. This glaring mismatch is known as the missing satellites problem. Where did all these predicted small halos go? One compelling idea is that the first generations of stars were incredibly violent. Their intense radiation and the shattering explosions of the first supernova created powerful winds that swept through the primordial gas. In the smallest, most vulnerable dark matter halos, this cosmic gale could have blown away every last shred of star-forming fuel. These halos were left intact, their dark matter scaffolding still in place, but with no gas to ignite into visible stars. They became ghost halos, invisible islands of pure dark matter drifting through the galactic sea. The dwarf galaxies we can see are the lucky survivors, the ones massive enough to hold onto their gas and light up, and these visible dwarfs tell a shocking story of their own. Measurements of the motions of stars within them reveal that they are overwhelmingly dominated by dark matter. Their mass-to-light ratios are astonishingly high, meaning for every bit of light their stars produce, they possess a tremendous amount of unseen mass. In some cases, dark matter outweighs normal matter by thousands to one. These galaxies are not just sprinkled with dark matter, they are defined by it, offering a pure and undiluted view of its gravitational effects. This makes them perfect for testing the fundamental nature of the dark matter particle itself. For instance, the most popular model, cold dark matter, predicts that halos should have very dense, cuspy centers. Yet observations of some dwarf galaxies suggest their dark matter cores are softer and more spread out. This tiny discrepancy on the smallest scales is a massive clue. It challenges physicists to consider if dark matter is perfectly cold and slow-moving, or if it might have some slight intrinsic motion, making it slightly warm, which would prevent it from clumping too densely. It could even hint at more exotic possibilities, like dark matter interacting with itself in ways we have not yet imagined. By studying the faint, trembling motions of stars in these galactic fossils, we are conducting a stringent test of the dark matter paradigm itself. The mysteries hidden within the smallest galaxies are imposing powerful constraints on our largest theories, forcing us to refine the blueprint of the cosmos. Deep within the faint glow of a dwarf galaxy, a subtle but profound mystery unfolds. It is a puzzle that challenges the very foundations of our cosmic blueprint, known as the Core-Cusp Problem. Sophisticated computer simulations, which model the behavior of cold dark matter, produce a very specific prediction for the shape of a dark matter halo. The invisible material should pile up dramatically toward the galactic center, creating a sharp density peak, or a cusp. The gravitational pull at the very heart of a galaxy should be incredibly intense. Yet when astronomers measure the rotation of stars in many faint dwarf galaxies, they find something entirely different. The data suggests a gentle central region, a plateau of constant, lower density known as a core. It is as if the central city of a metropolis was mysteriously less crowded than its outer suburbs, defying all expectations of how gravity should arrange the unseen mass. This is not a minor accounting error. It is a direct tension between our most powerful theoretical models and the hard evidence written in the motions of stars. The cold dark matter paradigm, which so perfectly builds the cosmic web on large scales, appears to falter on the intimate scale of a small galaxy. What could be causing this unexpected smoothing of the galactic core? One compelling possibility is that dark matter is not entirely aloof. Perhaps the particles can interact with one another through some unknown force, a faint self-interaction. If dark matter particles can scatter off each other like billiard balls in the cosmic dark, these tiny collisions would transfer energy from the crowded outskirts toward the center. Over billions of years, this process could gradually erase the sharp central cusp, redistributing the mass to form a much smoother core. The alternative solution looks not to the dark sector, but to the violent drama of stellar life and death. Imagine the first generations of stars in a young dwarf galaxy. These are often colossal, short-lived giants that end their lives in cataclysmic supernova explosions. These blasts drive powerful winds, creating immense outflows of gas that slam outward from the galactic center. This cyclic fury, this repeated pushing and pulling of normal matter, could act like a gravitational paddle. As vast plumes of gas surge out, they tug gravitationally on the dark matter, effectively stirring it and scattering it outward. Over eons, this astrophysical feedback could carve out the observed core, using the force of starlight itself to sculpt the invisible foundation. This puzzle forces a remarkable evolution in our quest. It drives theorists to invent more nuanced models of what dark matter could be, and it pushes observers to gather ever more precise data from the faintest galaxies. The Core-Cusp Problem is not a failure of science, but a sign of its progress. It is the friction point where our simple blueprint meets the complex reality of the cosmos, demanding that we look deeper to understand the true architect of the galactic form. The silent framework of dark matter is not an unyielding monolith. It listens. The relationship between the invisible architecture and the luminous matter it cradles is a profound conversation, a dynamic interplay of push and pull across cosmic time. While dark matter provides the initial gravitational stage, the actors upon it, the stars and black holes, possess a power to reshape the theater itself. This is the concept of feedback, where the energy output of ordinary matter echoes back to influence its dark foundation. The cycle often begins with the most dramatic of stellar events. When a massive star exhausts its nuclear fuel, its core collapses in a cataclysmic supernova explosion. This detonation unleashes more energy in a few moments than our sun will emit in its entire lifetime. The blast drives colossal winds, hurling the outer layers of the star outward at thousands of kilometers per second. These winds slam into the surrounding galactic gas, pushing it outward in a vast, energetic outflow. This is not just a movement of gas. Through the unbreakable chain of gravity, the expulsion of this immense mass exerts a gravitational tug on the dark matter halo. It acts like a cosmic paddle, stirring the invisible particles and scattering them slightly outward from the center. Over eons and through many such stellar cycles, this process can gradually carve out a smoother, less dense core in the dark matter distribution, directly addressing the puzzle of the Core-Cusp Problem in dwarf galaxies. But there is an even more powerful agent of change dwelling in the hearts of most large galaxies, a supermassive black hole with a gravitational grip so fierce that not even light can escape. When such a behemoth actively feeds on surrounding gas, it does not do so quietly. The infalling matter swirls into an intensely hot, bright disk, and the black hole can launch jets of charged particles and radiation that stretch for thousands of light years. This phenomenal release of energy, seen from afar as a quasar or active galactic nucleus, floods the central galaxy with a torrent of heat. This heat is so intense that it can prevent the vast reservoirs of galactic gas from cooling down and collapsing to form new stars. It effectively puts a ceiling on the galaxy's growth, a process known as feedback regulation. The gravitational repercussions are profound. By heating the gas and preventing it from settling into the central depths of the dark matter halo, this active nucleus alters the mass distribution at the galaxy's core. The dark matter, which responds only to gravity, finds its central concentration subtly smoothed and redistributed by the furious activity of the black hole it helped to form. The final structure of a galaxy is therefore not simply the result of a pre-drawn dark matter blueprint. It is a co-creation, a product of the initial gravitational foundation and the subsequent, sometimes violent, astrophysical renovations carried out by the stars and black holes that call it home. The invisible framework is not a rigid scaffold, but a responsive participant in the luminous drama of galactic life. But what if the entire premise is wrong? A small but persistent group of scientists argues that we are not missing matter, but missing the point about gravity itself. Their alternative is known as modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the 1980s, MND offers a radically different solution. It suggests that Isaac Newton's famous laws, which work so perfectly within our solar system, begin to break down in the profound gravitational weakness of a galaxy's outer edges. In these regions, the acceleration from gravity becomes vanishingly small, falling below a critical threshold. MND proposes that at these ultra-low accelerations, the force of gravity strengthens, becoming slightly more powerful than Newton's laws would predict. This single, elegant modification produces a startling result. It perfectly explains the flat rotation curves of spiral galaxies, making stars in the outer regions orbit faster without needing a single gram of invisible dark matter. For individual galaxies, MND is remarkably successful, matching the observed data with striking accuracy using only the visible stars and gas. Yet this elegant theory faces its own monumental challenges. Its most significant difficulty lies in explaining cosmic phenomena where the gravitational source is completely divorced from visible matter. The most famous example is the Bullet Cluster, a spectacular cosmic collision of two galaxy clusters. When astronomers mapped this system, they found something man cannot easily explain. The visible matter, the hot X-ray gas from the clusters, was slowed and stuck in the middle of the collision. But the gravitational lensing map, which shows where the majority of the mass actually lies, was clearly displaced. The peak of the gravitational field was not with the galaxies, but ahead of them, in a region seemingly empty of light. This is a direct signature of a substance that does not interact with normal matter, that passed straight through the cosmic wreckage. It behaves exactly like a cloud of collisionless dark matter. While MIND can be tweaked and adjusted, it struggles to account for this and other large-scale evidence, such as the precise pattern of the cosmic microwave background or the overall structure of the cosmic web. The result is a scientific standoff of profound importance. On one side, the dominant theory of an invisible particle that builds cosmic structures but remains stubbornly undetected. On the other, a modification to one of physics' most cherished laws that works beautifully in galaxies but falters on the largest scales. This vibrant debate is not a weakness, but a sign of a healthy and self-critical science, forever probing its own foundations in the pursuit of a deeper truth. The Bullet Cluster offers a cosmic crime scene where the evidence for dark matter is laid bare. Imagine two immense families of galaxies, each containing hundreds of members, passing through one another in a collision that unfolds over hundreds of millions of years. In such a tremendous event, the different components of the clusters behave in strikingly different ways. The most abundant form of ordinary matter is not the stars themselves, but a superheated gas that fills the space between galaxies. This gas glows intensely in X-rays, and when the clusters collide, this gas behaves like a fluid. The clouds of gas slam into each other, creating immense friction and pressure that slows them down dramatically. They become stuck in the middle of the cosmic wreck. The visible galaxies, vast as they are mostly empty space. Like swarms of bees passing through one another, the stars and their dark matter halos are so spread out that they continue on their paths largely unaffected, drifting apart on the other side of the collision. This is where the true detective work begins. Using the phenomenon of gravitational lensing, astronomers created a map of the cluster's total mass, a map that reveals where gravity is strongest. The result was stunning. The peaks of gravitational mass were not in the center with the piled-up, glowing gas. They were located in two regions flanking the center, perfectly aligned with the congregations of visible galaxies that had passed through. This is the smoking gun. The majority of the mass, the true source of gravity, is completely divorced from the ordinary matter. It is a substance that felt no friction, that did not slow down, and that passed through the entire collision as if it were not even there. This is the exact behavior predicted for dark matter. Modified gravity theories struggle profoundly with this evidence. They attempt to explain galactic rotation by tweaking the laws of physics, but they have no simple way to account for gravity being strongest where there is no visible matter to generate it. The Bullet Cluster shows us dark matter not as a theoretical idea, but as a physical reality, a substance that can be separated from the normal atoms of the universe. It reveals the hidden architecture in motion, demonstrating that the cosmic blueprint is built from a material that is both substantial and profoundly detached from the light we see. The true scale of dark matter's dominance becomes undeniable within a galaxy cluster. Think of these colossal structures not as simple collections of galaxies, but as immense cities built upon a foundation of invisible mass. The hundreds or even thousands of gleaming galaxies you see in a cluster image are merely the glittering streetlights of this cosmic metropolis. They account for less than 5% of the total mass. The true bulk of the city, its infrastructure and population, remains unseen. The next largest component is a vast, seething ocean of superheated gas that fills the space between the galaxies. This intracluster medium is so incredibly hot, reaching tens of millions of degrees, that it glows not in visible light, but in a brilliant, high-energy X-ray haze. What could possibly heat gas to such an extreme temperature? The answer is the overwhelming gravitational crush of the cluster's primary constituent, its dark matter halo. This invisible architecture, making up roughly 85% of the cluster's total weight, creates a gravitational well so deep that any gas falling into it is compressed and heated to staggering temperatures, a perpetual testament to the power we cannot see. This makes clusters the ultimate natural laboratories for studying dark matter, not just through their gravity, but through their light. The hot gas acts as a tracer, outlining the shape of the deep dark matter potential well that contains it. Furthermore, the sheer concentration of mass in a cluster warps the fabric of space-time so dramatically that it becomes a powerful gravitational lens. It magnifies and distorts the light from galaxies that lie far behind it, acting as a natural telescope that allows us to peer deeper into the cosmos than we ever could alone. By analyzing these distorted arcs of light, we can create a precise map of the cluster's total mass, revealing the distribution of the dark matter skeleton with stunning accuracy. The very existence and structure of these clusters are a direct result of the dark matter blueprint. They mark the densest nodes, the grand central stations of the cosmic web. Their number and how they have grown over cosmic time provide a strict test for our cosmological models. When we observe a galaxy cluster, we are witnessing the ultimate expression of dark matter's gravitational rule, a metropolis where the invisible framework not only defines the city limits but also dictates the very climate within its streets. The faint afterglow of the Big Bang holds a frozen music from the dawn of time. This cosmic microwave background is not a perfectly smooth curtain of light. It is textured with minute variations in temperature, the faintest of whispers from the universe's first moments. These whispers are the imprints of sound waves that once rippled through the primordial cosmos. In that incredibly dense and hot early state, the universe was a seething sea of light or photons and the raw material of atoms known as baryonic matter. This ordinary matter and light were locked in a relentless struggle, with radiation pressure pushing the matter apart while gravity tried to pull it together. The result was a series of massive pressure waves, true sound waves on a cosmic scale, that propagated outward through the fiery plasma. But this luminous drama was unfolding within a pre-existing and entirely passive sea of dark matter. While the photons and baryons pushed and pulled against each other, the dark matter, unaffected by the intense radiation, simply sat there, providing a gravitational anchor. It was the silent stage upon which this sonic performance played out. Then, about 380,000 years after the Big Bang, the universe cooled just enough for a monumental change. Electrons and protons combined to form the first neutral atoms. In an instant, the photons were set free, no longer constantly colliding with matter. They streamed across the universe, and we see their released light today as the cosmic microwave background. At that precise moment, the cosmic sound waves froze in place. The ripples in the plasma became permanent wrinkles in the distribution of matter. This event imprinted a specific, preferred scale onto the cosmos, a distance of about 500 million light-years. This is the Baryonic acoustic oscillation, a fossilized echo of the universe's first sound. How do we detect this ancient echo today? We see it in the grand maps of the cosmic web. When astronomers survey the positions of millions of galaxies, they find a subtle but consistent statistical preference. There are more pairs of galaxies separated by that exact 500 million light-year scale than by any other distance. It is as if the universe has a built-in standard ruler, a recurring spacing that stems directly from those frozen sound waves. By carefully measuring this BAO ruler at different cosmic epochs, we can trace the expansion history of the universe with phenomenal precision. More profoundly, this signal confirms that the dark matter scaffolding was already firmly in place, dictating the gravitational landscape long before the first stars ever shone. The Baryonic acoustic oscillation is not just a fossil, it is the original calibration mark on the dark matter blueprint, a fundamental signature that our entire cosmic structure was born from a specific set of initial conditions written into the fabric of reality itself. These digital universes begin as a vast, uniform grid, a sea of tens of billions of virtual dark matter particles. Each particle represents a colossal clump of this unseen substance, a single thread in the cosmic tapestry. The simulation seeds this grid with the exact same tiny density fluctuations we observe etched into the cosmic microwave background. Then, with a press of a button, the clock starts. The supercomputer unleashes the immutable force of gravity, calculating the subtle pull between every single one of those billions of particles. Over millions of processor hours, the simulation fast-forwards through billions of years of cosmic evolution. What begins as a nearly smooth grid begins to knot and wrinkle. Gravity amplifies the slightest over densities, pulling dark matter into a sprawling, filamentary web. At the intersections of these virtual filaments, dark matter halos condense like dew on a spider's web, growing over time as they merge with smaller neighbors. The most advanced simulations, like Illustris TNG and Eagle, go a crucial step further. They weave the story of ordinary matter into this dark foundation. They model the complex physics of gas cooling, star formation, and the explosive feedback from supernova and supermassive black holes. We can watch, in stunning visualizations, as a swirling disk of gas settles within a dark matter halo, igniting into a spiral galaxy. We can witness two virtual galaxies collide, their stars flung into chaotic orbits to form an elliptical galaxy, exactly as our telescopes observe. These simulations act as a rigorous testing ground for our theories. When a simulation that assumes perfectly cold, collisionless dark matter produces dwarf galaxies with overly dense centers, it highlights the real-world Core-Cusp Problem. When it predicts a swarm of tiny dark halos that never light up with stars, it throws the missing satellites problem into sharp relief. This forces physicists to refine the model, perhaps by giving dark matter a slight warmth or a faint ability to interact with itself. By constantly comparing the digital cosmos to the real one, these vast experiments allow us to reverse engineer the properties of the invisible particle itself. They are not just animations, they are predictive instruments, digital laboratories where we can run the history of the universe over and over again, each time tweaking the fundamental rules to see which set of laws builds a cosmos that looks exactly like our own. Just as the cosmic web reaches its magnificent scale, a counterforce emerges on the grandest stage of all. While dark matter's gravity tirelessly builds the universe's great structures, a mysterious repulsive force is actively tearing them apart. This is dark energy, the most dominant component of our cosmos and perhaps its greatest mystery. Its discovery in the late 1990s sent shockwaves through the world of astronomy. Two independent teams were studying distant stellar explosions, known as Type 1, a supernova, to measure how the universe's expansion rate had changed over time. Everyone expected to find that the pull of gravity from all the matter in the cosmos was slowing the expansion down. Instead, the data revealed the exact opposite. The most distant supernova were fainter than predicted, meaning they were farther away than anyone had thought. The expansion of the universe was not slowing, it was accelerating. Something was overwhelming gravity itself, pushing galaxies apart at an ever-increasing rate. This something, dubbed dark energy, is now calculated to make up about 68% of the total energy content of the universe. It is the primary force shaping the cosmos's ultimate destiny. But what could it possibly be? The leading, though deeply strange, explanation points to the very fabric of empty space itself. According to quantum physics, a vacuum is not truly empty. It is a seething foam of virtual particles that flicker in and out of existence. This quantum activity endows every cubic centimeter of space with a fundamental energy, a constant background hum. If this vacuum energy possesses a specific property, a negative pressure, then it would generate a repulsive gravitational effect. It would push space itself apart. This is the simplest interpretation of dark energy, but it comes with a staggering problem. When theorists calculate the expected value of this vacuum energy, the result is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the history of science. This colossal mismatch tells us that our understanding of the quantum vacuum and gravity on cosmic scales is profoundly incomplete. The true nature of dark energy remains one of the most profound puzzles in physics, yet its influence is undeniable, creating a cosmic tug-of-war that defines our current era. On one side, dark matter works to clump and concentrate the universe into galaxies and clusters. On the other, dark energy works to smooth and dilute the cosmos, driving everything apart. We exist in a brief and precious window of cosmic time where these two titanic forces are nearly in balance, allowing for the rich structure we see around us. But this balance is temporary. If dark energy behaves as a constant vacuum energy, its influence will only grow as the universe expands and becomes more empty. Billions of years from now, its push will become so dominant that it will begin to unravel the cosmic architecture. First, it will tear apart the great clusters of galaxies. Then, the gravitational bonds holding individual galaxies together will be overcome. In a far distant future, even stars and planetary systems could be ripped apart in a hypothetical finale known as the Big Rip. The invisible blueprint of dark matter exists on a canvas that is relentlessly stretching, a dynamic stage where the very rules of the game are still being written. Deep underground, in the profound silence of abandoned mines and beneath mountains, the hunt for a ghost is underway. These laboratories are cathedrals of quiet, shielded from the constant rain of cosmic rays by a mile of solid rock. Their mission is to listen for the faintest of sounds, the hypothetical bump of a dark matter particle against the ordinary matter of our world. At the heart of experiments like LUX Zeppelin, Panda X, and Xenon NT are immense vats containing tons of ultra-pure liquid xenon, chilled to a state of perfect stillness. The hope rests on a fleeting, almost impossible event. If a WIMP, a weakly interacting massive particle, drifts through this tank, there is a tiny chance it will not pass through unnoticed. Instead, it might graze the nucleus of a xenon atom. This minuscule collision would create two telltale signatures, a quick flash of scintillation light and the release of a single, free electron. To witness such an event is to look for a single raindrop falling in a vast, dark ocean. The detectors are therefore miracles of sensitivity, their walls lined with arrays of photomultiplier tubes that can amplify the faintest glimmer into a measurable signal. The entire system is engineered to distinguish this potential whisper from the constant, dull roar of natural background radiation from the rocks, the air, and even the detector materials themselves. Every other possible source of energy must be identified and discarded, leaving only the pristine signature of the unknown. Yet after years of searching, the silence persists. No definitive, reproducible signal has emerged from the darkness. This ongoing null result is not a failure, but a process of profound elimination. Each experiment that hears nothing is actually telling us something crucial about what dark matter is not. The continued quiet is placing ever more stringent limits on the possible mass of WIMP and the ludicrously weak force with which they must interact. We are drawing a tighter and tighter circle around the possible identity of this phantom, ruling out vast swaths of theoretical territory. This great silence is now pushing physicists to think more creatively, to consider candidates beyond the traditional WIMP, like the wave-like action or even more exotic possibilities. It also drives the design of next-generation detectors that will be larger, colder, and even more isolated, probing the shadows for fainter and fainter whispers. The direct detection of a single dark matter particle would be a moment that transforms human knowledge, finally putting a face to the universe's primary architect after a century of searching. While underground labs listen for a direct collision, other observatories scan the cosmos for the ghost's faint echo. This is the hunt for indirect detection, a search not for the dark matter particle itself, but for the luminous aftermath of its destruction. The strategy rests on a compelling possibility. What if dark matter is its own antimatter counterpart? If this is true, then whenever two of these phantom particles collide, they could annihilate each other in a flash of pure energy. This violent conversion would produce a spray of familiar, detectable particles, a cosmic flare signaling the presence of the invisible. The most telling signature would be a burst of high-energy gamma rays, the most powerful form of light. Our eyes are on the sky with instruments like the Fermi Gamma Ray Space Telescope constantly scanning for this telltale signal. But where should we look? The best hunting grounds are places where the dark matter is most densely packed. Scientists point their virtual telescopes toward the hearts of galaxies, where the gravitational pull is strongest, and especially toward the faint, dark matter-dominated dwarf galaxies that orbit our own. These pristine dwarfs are perfect targets because they lack the stellar factories like pulsars that could produce similar gamma-ray signals, offering a cleaner view into the dark. Yet the search is fraught with ambiguity. A few years ago, astronomers noticed a puzzling excess of gamma rays emanating from the center of our own Milky Way. The pattern was intriguing, matching what some models predicted for dark matter annihilation. But was it the smoking gun? Further analysis suggested it could also be explained by a previously unseen population of rapidly spinning stellar corpses known as millisecond pulsars. The signal, while tantalizing, remains inconclusive. The search extends beyond light to the most elusive particles of all, neutrinos. Deep in the clear ice at the South Pole, the Ice Cube Observatory functions as a colossal particle trap. Its thousands of optical sensors watch for the faint blue glow created when a high-energy neutrino, born from a hypothetical dark matter annihilation in the core of the Sun or Earth, interacts with the Antarctic ice. So far, the definitive flash has not been found. These indirect searches are a delicate exercise in cosmic forensics. Every unusual signal must be scrutinized, every potential astrophysical imposter ruled out. The challenge is immense, but the promise is profound. To witness the death throes of a dark matter particle would be to finally understand the fundamental physics of the hidden architecture, revealing not just its presence, but its deepest nature through the light it leaves behind. Beneath the Swiss-French border, a circular tunnel 27 kilometers long houses a different kind of dark matter search. This is the Large Hadron Collider, where physicists do not wait for dark matter to come to them. They attempt to create it from pure energy, by accelerating protons to within a whisper of light speed and smashing them together. The LHC recreates the violent, high-energy conditions that existed a fraction of a second after the Big Bang. It is a time machine for the fundamental forces of nature. Within the debris of these microscopic fireballs, new particles can flash into existence, particles not seen since the universe's first moments. If dark matter particles are light enough and coupled to ordinary matter by even the faintest of forces, they could be born here. But how do you see something that is fundamentally invisible? The answer is written in the language of missing energy. When two protons collide, the total energy and momentum going into the event must equal the total energy and momentum carried away by all the resulting particles. This is a fundamental law of physics. Experiments like ATLAS and CMS are colossal, layered detectors that act as microscopic cameras, capturing the identities and trajectories of every known particle that erupts from a collision. Sometimes they record an event where a significant amount of energy seems to simply vanish. The detector sees a spray of familiar particles jetting out in one direction, but the event as a whole is unbalanced, as if an unseen particle carried away energy and momentum without leaving a trace. This missing energy is the ghostly signature of a dark matter particle fleeing the scene. indifferent to the complex machinery built to detect it. The LHC's triumphant discovery of the Higgs boson proved it could reveal new physics, but the dark matter particle remains elusive. No definitive missing energy signal has yet risen above the background noise of known processes. Yet this absence is itself a powerful result. Each unsuccessful search rules out vast territories of possibility, entire families of theoretical dark matter models that are now crossed off the list. This process of elimination is relentlessly guiding theorists, forcing them to refine their ideas and explore more exotic or subtle possibilities. The collider's true power lies in its relentless push against the energy frontier, creating conditions never before seen on Earth, hoping that in the next billionth of a second, the universe's hidden architect will finally step into the light. Our most precise measurements of the cosmos are now in direct conflict. This is the Hubble tension, a stubborn discrepancy that is shaking the foundations of modern cosmology. On one hand, we have the pristine snapshot of the infant universe, the cosmic microwave background. By analyzing its subtle patterns, scientists can calculate the universe's expansion rate, known as the Hubble constant, with incredible precision. This method gives us one number. On the other hand, we have a cosmic distance ladder built from brilliant markers in our modern universe, like Cepheid variable stars and Type 1, a supernova. These celestial beacons allow astronomers to measure how fast galaxies are receding from us right now. This method consistently gives a higher, faster value for the Hubble constant. The two most trusted ways of measuring the universe's expansion disagree, and the gap is not shrinking with better data. It is a genuine crisis. This is not a simple miscalculation. It suggests that our standard model of the universe, known as lambda CDM, which beautifully incorporates both dark energy and cold dark matter, might be incomplete. Perhaps dark matter is not perfectly simple and cold. Maybe its properties changed over cosmic history, evolving in a way that subtly altered the expansion rate. Another compelling idea is an early form of dark energy, a temporary repulsive force that surged in the universe's first epochs, giving expansion an extra push that our current models do not account for. Resolving this tension is not just about getting the numbers to match. It is a direct test of the cosmological framework that defines dark matter's role. If lambda CDM is flawed, then our entire interpretation of the dark matter blueprint, from the formation of the first galaxies to the shape of the cosmic web, might require a profound revision. The Hubble tension is a powerful reminder that our map of the cosmos is a living document, still being drawn and constantly challenged by the very universe it seeks to explain. The silent architecture of dark matter may outlast every star in the sky. The long-term destiny of our universe rests on a delicate balance between two invisible titans, the gravitational pull of dark matter and the repulsive push of dark energy. In our current era, we exist in a brief, vibrant window where these forces are nearly matched, allowing for the brilliant tapestry of galaxies to form. But this balance is temporary. Cosmological models suggest that dark energy's influence will only grow as the universe expands and becomes more empty. In the far, far future, its accelerating push will become completely dominant. The first consequence will be a profound cosmic isolation. Over trillions of years, every galaxy not gravitationally bound to our own local group will be swept beyond the cosmic horizon. Their light will fade, and they will vanish from the observable universe forever, leaving our galactic neighborhood alone in an immense, expanding void. Within this isolated group, the age of star formation will also draw to a close. All the interstellar gas, the raw material for new suns, will eventually be locked away inside dead stellar remnants or consumed by black holes. The last stars will flicker out, leaving the cosmos dark and cold. What remains is a cosmic graveyard populated by black holes, which themselves are not permanent. Over almost unimaginable timescales, these gravitational giants will slowly evaporate, radiating away their mass through a process known as Hawking radiation. Yet through this entire cosmic winter, the dark matter halos of galaxies will endure. Their gravitational bonds, woven from a substance that feels no other force, will remain intact long after the last black hole has dissipated into a faint whisper of radiation. This invisible architecture could be the final, permanent structure in the universe. However, this eternal future is not guaranteed. It hinges on a single, still unverified property of dark matter, its perfect stability. What if dark matter is not truly forever? If the particles that compose it can decay, even over eons that make the current age of the universe seem like a blink, then the cosmic blueprint itself could slowly fade. Such a decay would inject a faint trickle of energy into the cold, dark cosmos, potentially altering the final chapters of existence in ways we can scarcely model. The ultimate fate of everything, from the grandest galaxy cluster to the ghostly dark matter halo of a single dwarf, depends on the fundamental physics of a particle we have yet to identify. The hidden blueprint may be the universe's most enduring monument, or it may carry a silent expiration date written into its very nature. This hidden architecture may be the very reason we are here to ponder it. The universe seems curiously fine-tuned for life, a fact that leads us to a profound question. Could we exist without dark matter? The anthropic principle offers a compelling perspective, suggesting that the universe we observe must have physical properties that allow for the existence of conscious observers. Remove one key ingredient like dark matter and the cosmic recipe for life fails. In a hypothetical universe without this invisible scaffolding, the formation of cosmic structure would have been a sluggish, inefficient affair. The initial gravitational seeds, those faint ripples from the Big Bang, would have grown far too slowly without the immense gravitational pull of dark matter to accelerate the process. Galaxies might not have formed early enough or grown massive enough to forge the essential elements of life. The first generations of stars are the universe's great factories, nuclear furnaces that fuse primordial hydrogen and helium into heavier elements like carbon, oxygen, and iron. Without the deep gravitational wells of dark matter halos to rapidly draw in gas and trigger star formation, this cosmic enrichment would have been a trickle instead of a flood. The universe would be a much poorer place, lacking the raw materials for planets, oceans, and living organisms. Furthermore, the stable, ordered structure of a spiral galaxy like our Milky Way is a direct gift of its dark matter foundation. This stable disk provides a long-lived, relatively quiet neighborhood for planetary systems to coalesce and evolve over billions of years of calm. A chaotic, unstable galaxy would constantly bombard fledgling worlds with radiation and gravitational disruptions, making the sustained, delicate evolution of life nearly impossible. So when we look up at the night sky and wonder about our place in the cosmos, we are not just observers of the dark matter blueprint. We are a potential consequence of it, a living testament to the specific cosmic conditions that this hidden architecture makes possible. Our existence may be woven into the fabric of the unseen. Yet even as this blueprint explains the grand cosmic web, its details appear to blur on the smallest of scales. These are the small-scale crises, a collection of stubborn puzzles where our best simulations of cold dark matter do not quite match the quiet reality we observe. We have already encountered the missing satellites, the ghost halos that never lit up, and the Core-Cusp Problem, where the hearts of dwarf galaxies are mysteriously smooth. But a third challenge is perhaps the most telling of all. It is called the too big to fail problem. Supercomputer models predict that the most massive dark matter subhalos orbiting a galaxy like our Milky Way should be incredibly dense, their gravitational wells deep enough to easily attract gas and form bright, bustling satellite galaxies. Yet when we look at the actual satellites around us, they seem to reside in much lighter, less massive halos. The most massive predicted subhalos appear to be completely dark, failing to host the brilliant galaxies their immense gravity should demand. This is not a minor oversight. It suggests a fundamental tension between our theoretical blueprint and the finished galactic structure. One compelling solution is that we may have the basic nature of the dark matter particle slightly wrong. Perhaps it is not perfectly cold and slow-moving, but slightly warm. In a warm dark matter model, the particles would have a small amount of intrinsic motion, a slight fever from the early universe. This motion would prevent dark matter from clumping on the very smallest scales, effectively smoothing out the formation of those overly dense subhalos and producing a distribution that better matches the faint satellite galaxies we see. Another fascinating possibility is that dark matter is not entirely aloof. What if these phantom particles can interact with each other through some unknown force? This is self-interacting dark matter. If dark matter particles can scatter off one another like billiard balls in the cosmic dark, these gentle collisions would transfer energy. Over time, this would erase the dense central cusps in small halos, carving out the softer cores we observe and potentially explaining why the most massive subhalos are not as dense as predicted. Yet there is another, equally powerful explanation that looks not to the dark but to the light. The immense complexity of ordinary matter, what scientists call baryonic physics, might hold the key. The cycle of star formation is not a gentle process. When the first massive stars in a small halo explode as supernova, their colossal energy drives powerful winds that can blast the galaxy's gas far into space. This sudden loss of normal matter has a profound gravitational consequence. As the gas surges out, its gravitational tug pulls on the dark matter, effectively stirring it and scattering it outward from the center. This astrophysical feedback could be the cosmic sculptor, smoothing the dark matter core and even preventing some of the most massive halos from ever gathering enough gas to become visibly bright. Solving these small-scale mysteries is not about proving dark matter wrong. It is about refining the blueprint, understanding the intricate dialogue between the invisible foundation and the luminous world it supports. The answers will complete our picture of the galactic architect, revealing whether its hand is guided by simpler rules or by a physics far more complex than we ever imagined. Perhaps the phantom particle is not perfectly cold but carries a faint warmth from the dawn of time. This is the compelling idea behind warm dark matter, a subtle tweak to the standard model that could resolve the persistent small-scale puzzles. In this scenario, the dark matter particles were born with significant thermal motion, moving at relativistic speeds in the universe's fiery youth. This inherent jitter, this slight fever, has a profound consequence for the cosmic blueprint. As these warm particles streamed freely through the early cosmos, their motion acted like a cosmic iron, smoothing out the tiniest wrinkles in the dark matter fabric. The smallest density fluctuations were effectively erased, unable to collapse under their own gravity. This single property offers elegant solutions to two major problems. First, it naturally explains the missing satellites by preventing the formation of a vast swarm of the very smallest dark matter clumps. Warm dark matter predicts a much sparser population of dwarf galaxies, one that aligns more closely with the number we actually observe. Second, that same particle motion would prevent dark matter from piling up into sharp, dense cusps at the centers of halos. Instead, it would produce the softer, cored central densities we see in many dwarf galaxies, directly addressing the Core-Cusp Problem. A leading candidate for this warm phantom is the sterile neutrino, a hypothetical particle that interacts only through gravity, making it even more elusive than its known relatives. Yet this elegant theory faces its own stringent test. The same smoothing effect that solves one mystery might create another. If warm dark matter suppresses small-scale structure too aggressively, it could prevent the formation of the very faintest dwarf galaxies we have already discovered. The existence of these ultra-faint dwarfs, these ghostly collections of stars that are incredibly rich in dark matter, places a tight constraint on just how warm the dark matter can be. The ongoing hunt for more of these faint galactic fossils becomes a critical experiment. Finding a population of very low mass, dark matter-dominated galaxies would challenge the warm dark matter model, while their continued absence would lend it strong support. This vibrant debate between cold and warm dark matter is far more than academic. It demonstrates how the fundamental properties of a single, unseen particle, its mass, its velocity, its birth in the first moments, are permanently stamped into the grand architecture of galaxies and the faintest whispers of their smallest companions. The cosmos is conducting a particle physics experiment on a galactic scale, and we are only learning how to read the results. Another layer of complexity emerges from the phantom blueprint itself. Perhaps dark matter is not entirely solitary. Within self-interacting dark matter models, these ghostly particles could occasionally collide with one another through a new, unknown force. Think of a vast, dark crowd where individuals can gently bump into each other, exchanging energy as they pass. This subtle scattering would act like a form of heat transfer, warming the dense, crowded center of a dark matter halo. Just as warm air rises and circulates, this thermal energy would push particles outward from the core, redistributing the invisible mass and smoothing the sharp central cusp into a gentler, flatter core. This single, elegant microphysical process could directly resolve the puzzle of why many dwarf galaxies lack a dense central peak. Furthermore, these gentle collisions would tend to make the inner regions of a halo more symmetrical, more spherical, a prediction that astronomers can test by carefully mapping the shapes of galactic cores. Yet this intriguing idea must contend with the evidence from cosmic collisions like the Bullet Cluster. There, the dark matter components of two galaxy clusters passed through one another almost without a whisper of interaction. This tells us that if self-scattering does occur, it must be an exceedingly rare event. The force mediating it must be incredibly feeble, allowing dark matter to remain largely aloof even from itself. Current research focuses on threading this needle, running sophisticated supercomputer simulations to see if a weakly self-interacting model can successfully sculpt the diverse galactic cores we observe without violating the stringent limits set by clusters. This possibility adds a profound new dimension to the hidden architecture, suggesting that the universe's primary building material may have a rich internal life of its own, governed by rules we are only beginning to guess. At the opposite end of the spectrum lies a possibility so strange it reimagines the phantom itself. This is fuzzy dark matter, a model where the building blocks of the cosmic architecture are not heavy particles, but whispers of almost nothing. Imagine a substance composed of particles so incredibly light that billions of them would be needed to equal the mass of a single electron. At this scale, the rules of the quantum world take over. Each particle is no longer a tiny speck, but behaves as a diffuse wave, its presence smeared across a vast volume of space. This is the de Broglie wavelength, a quantum effect that, for these ultra-light particles, becomes enormous, stretching across entire dwarf galaxies. The result is a dark matter halo that is not a swarm of discrete points, but a single, coherent quantum wave. This wave, like nature, has a dramatic consequence for the cosmic blueprint. It naturally erases the smallest wrinkles in the dark matter fabric. The formation of very small, dense clumps is suppressed, as the waves simply cannot be squeezed into such a tight space. This offers an elegant, single solution to the small-scale crises, potentially explaining both the missing satellites and the smooth cores of dwarf galaxies without needing complex stellar feedback. The internal structure of such a halo would be unlike anything in the cold dark matter model. At its very heart, physicists predict a soliton, a stable, dense, standing wave of dark matter akin to a single, massive ripple held perfectly still by its own gravity. Surrounding this central soliton would be a complex pattern of interference fringes, like the ripples from multiple stones thrown into a pond, creating a subtle, shimmering texture throughout the galactic halo. Yet this beautiful idea faces its own observational hurdles. The specific scale on which structure is suppressed is tied directly to the particle's mass. Finding the right mass to match the diverse population of galaxies we see, from the faintest dwarfs to the largest clusters, is a delicate balancing act. Some simulations suggest that fuzzy dark matter might not produce enough faint satellite galaxies, or that the predicted solitons in dwarf galaxy centers might be too dense, creating gravitational effects we do not observe. The hunt is now on for the unique signatures of this wave-like phantom. Astronomers are scrutinizing the faintest galaxies for the telltale marks of a quantum wave halo, while laboratory experiments are being designed to detect the ghostly oscillations of these ultra-light actions. Fuzzy dark matter challenges the very idea of a particulate cosmos, suggesting instead that the universe's hidden architecture might be written not in stones, but in waves, a fundamental quantum field vibrating silently beneath the stars. The next generation of eyes on the cosmos are already opening, designed to see the invisible in ways we never could before. These are not just new telescopes, but entire observatories built with a single, profound purpose: to map the hidden architecture of the universe. The Vera Rubin Observatory in Chile will soon begin the legacy survey of space and time, a monumental 10-year project to scan the entire southern sky. Night after night, it will capture the faint, telltale warping of light from billions of galaxies, creating the most detailed chart of dark matter's distribution ever conceived. Its view will be complemented by the Euclid Space Telescope, a mission specifically engineered to probe the dark universe. From its vantage point in space, free from the blurring of our atmosphere, Euclid will measure the shapes of galaxies with phenomenal precision, tracing the subtle grip of dark matter's gravity across 10 billion years of cosmic history. And the Nancy Grace Roman Space Telescope will soon join this grand campaign, its wide-field vision offering another unparalleled window into the cosmic web. Together, these instruments will produce a flood of data so vast it will transform our understanding of the dark matter blueprint, revealing its intricacies from the largest filaments down to the scale of individual galaxy clusters. On the other side of the hunt, deep underground, the quest for the particle itself is entering a new era. Scientists are already designing the next generation of direct detection experiments, vats of liquid xenon or argon that will be orders of magnitude more sensitive than today's. These colossal underground laboratories will listen for whispers so faint they are currently drowned in silence. At the same time, the Large Hadron Collider is slated for upgrades that will increase its collision rate, boosting the chances of creating dark matter in the laboratory. This multi-pronged assault, from the cosmic to the microscopic, means the next decade promises to be a period of unprecedented discovery. We are not just hoping for a lucky break, we are building the tools that will systematically corner the phantom, either identifying it directly or painting it into such a tight corner that its fundamental nature can no longer hide. The golden age of mapping the unseen is just beginning, and its findings may force us to rewrite the cosmic blueprint from its very first lines. The mystery of dark matter pushes at the very boundaries of reality, into realms where physics becomes pure philosophy. The most speculative theories propose that our entire cosmos, with its specific dark matter blueprint, is not unique. It might be just one page in an infinite cosmic library known as the Multiverse. In the framework of string theory, our universe could be one of countless bubbles in a vast cosmic foam, each with its own unique set of physical laws and fundamental constants. In this breathtaking landscape, the amount and even the very nature of dark matter could be a random roll of the dice. In one universe, dark matter might be so sparse that galaxies never form. In another, it could be so abundant that it collapses everything into black holes almost instantly. We find ourselves in a universe with a very specific, finely tuned amount of this invisible substance, one that allows for the slow, graceful dance of galaxy formation and the eventual emergence of life. This observation dovetails with the anthropic principle, a simple yet profound idea. We can only observe a universe capable of producing observers. The hidden architecture of our cosmos, then, might not be a mandatory design. It could simply be the local bylaws of our particular cosmic neighborhood, one where the dark matter density is just right for stars, planets, and us to exist. While this multiverse concept is currently beyond the reach of experimental proof, it reframes our entire quest. It suggests that the puzzle of dark matter is not merely about identifying a missing particle within our universe, but about understanding why our universe has the specific properties it does. The silent framework beneath every galaxy could be a single, random expression of physics in a sea of infinite possibilities, a thought that stretches the meaning of our cosmic home to its absolute limit. Our journey through the hidden architecture of the cosmos brings us to a stunning realization. From Fritz Zwicky's first perplexing calculations to Vera Rubin's flat rotation curves, the evidence for an invisible framework has become undeniable. We have traced its gravitational signature in the warped light of distant galaxies, witnessed its ghostly presence in cosmic collisions like the Bullet Cluster, and mapped its vast filaments through the painstaking work of sky surveys. This is not a story of missing matter, but of a fundamental component of the universe, one that sculpts the grand cosmic web and cradles every galaxy within its gravitational embrace. The luminous splendor of stars and spirals is but the visible ornamentation on this profound, dark scaffold, while deep mysteries persist from the puzzling cores of dwarf galaxies to the troubling Hubble tension. These are not failures. They are the exciting frontiers where our understanding is being forged and refined. Each puzzle is a guidepost pointing the way toward a deeper truth about the nature of the phantom particle itself. As a new generation of telescopes and underground laboratories comes online, we are no longer merely inferring the blueprint. We are learning to read its language. The search for this hidden architect is more than a scientific endeavor. It is a fundamental expression of human curiosity, a quest to understand the very foundation upon which our universe and our place within it is built.